Hello everyone, and welcome back to a new episode of Silicon Zeros. In this episode, I don't think I've solved any new puzzles off camera, but I have done a fair bit of work optimizing the solutions to puzzles that were already solved. Mostly due to some conversation with Pleasing Fungus. Remember I solved Faux Reg with like 8 extra modules or something outrageous, like a 14 out of 6? He had given me a hint on that puzzle and said, if you want to solve that puzzle in 6 modules, try solving Shift 1 with just 9 modules. Now the ideal here is 10, and he's actually leaving it as 10 on purpose, even though it's possible with 9. I think because the solution with 9 is a little bit unsatisfying, and I'm not going to open this puzzle just yet. Well, maybe I should. Remember, this is the one where we had to like multiply by 10 and add 1, and so we had like 3 stages where there's, the stage where you read, the stage where you multiply, and the stage where you write. Pretty simple, right? What could we possibly remove? We needed everything. And I thought about this for some time, and I couldn't figure anything out. And he gave me another hint, which was enough to say, oh, of course, what an easy fix. He said to me, and so here, I haven't loaded this because this is the new solution. He said, what is equivalent to 2 2-slot registers? And the answer, of course, is 1 4-slot register. So we do need 3 stages, but we don't need a register for each stage. So this is basically the same solution as I had before, except that instead of having 1 register with 2 here and 1 register with 2 here, we just have a single register with 4 that feeds into itself. See, this goes here, and, well, it feeds into itself once, and then, why is it feeding into itself twice? I'm a little confused about that. But whatever, okay. So this is basically the improvement. I tried a bunch of stuff to, like, simplify this. In particular, one thing that seemed like it should be useful, I was like, maybe if we can have fewer stages by making the computation go faster, we wouldn't need that second register. It's something I was working on for a while. And, multiplication is very slow, right? It takes 8 ticks. And so there's a trick you can do. Trick is the wrong word. If you're multiplying by a constant, and multiplication is slow, you can reduce it to a bunch of additions. Because, okay, so what is 10, right, in binary? It's 8 plus 2. Well, we could get 2x by just adding x and x together. And you can get 4x by adding 2x and 2x together. And you can get 8x by adding 4x and 4x together. You add that with the previous 2x, and you have 10x. Right? So you can do addition in terms of multiplication, but... Sorry, multiplication in terms of addition. And for constants, that's actually usually pretty good. But here, multiplication is not slow enough to make that actually better. It's much worse. It takes the same number of ticks, but, like, you need to use 5 adders instead of 1 multiplier, I think. Maybe it was 4 adders, whatever. So anyway, not a profitable solution. But this idea of having a register that feeds into itself to create a delay, rather than feeding into another register, simplifies a lot of these multi-stage puzzles. So I did a couple of other improvements to existing solutions based on that. I think they're mostly in the asides. Oh, also, I talked about Grader with him. I showed him my solution to Grader. You know, haha, I'm so much smarter than you, and so on. He said he was just trying to find some way to squeeze out one more module, and complimented me on the wide equals up here, and having only 1 latch for this instead of 2 latches for these. And I realized, because he had said, like, wide equals and diff or clock or something like that together, I realized actually we can simplify this over here. Remember what we used to have was we were adding a 1 into here always, and then using the control signal from this to decide whether to use the new value, which is n plus 1, or the old value, which is n. But you can think about this as n plus 1 versus n plus 0, and we have a thing here that outputs either a 1 or a 0, depending on whether we should add. So you can just feed this directly as an input to the adder that's advancing the clock, and avoid the input selector on clock. And it still sort of feels like there ought to be some way, maybe, to simplify this clock. I couldn't find it. Pleasing Fungus notes that he was looking at ways to remove this 0, because I'm using the 0 in 2 places, right? Here and here. But this place isn't actually necessary. It doesn't need a 0. We will always, I think... Well, I was gonna say, we'll always have access to a 0 from somewhere. Because I was thinking one of these two would be 0. But that's not actually true. Right? If these are both 1, then we should be outputting a 0. And the input will be 2. So we can't just grab a 0 off of any of these. I don't know. He said in his email that this 0 was only needed to reset this diff. And so I assume he figured out some way to not need it here. But I'm not sure what that way was. Anyway, so that was greater. Got it down to 17 out of 22. Pretty good. What else did I do? Keypad? I went back and looked at keypad. Remember this one used to have 6 readers? We were just reading the literal values at 0, 1, and 2, and then like we had a base address we were reading a code from, and we added 1 to it, and we added 2 to it to decide where to write, and then like we sent that over to this guy. So I realized, hey, we can do the same trick with this delayed register, right? We'll just make one extra big register, and instead of like needing to read the address n minus 2 or n plus 2 or whatever, however you want to think about it, we can just read the address at base and have it sort of filter through this register until we have 3 adjacent values sitting right here. And then we compare each of them to the value in the key code, which is saved in these, which is not saved, we're being reread every time. And then we get all these zeros out, and everything's lovely. So this simplifies, this is the main improvement to my solution from last time. It also means we can avoid, no. I don't need the 3 anymore. I forget why I needed a 3. Oh, I remember now. Never mind. But I do actually need a 2, which is kind of frustrating. I really wish I could get rid of this 2. Not this 2, but this adder that uses 2 as an input. Because all it's doing is computing 2 plus the address that we started reading from, right? Here. And let me show you in the test. When we start writing something, this 3, you know, 2 plus 1, which is the address we started reading from. I mean, there's a 3 right here. We could just grab it, right? And this will always be equal to 2 plus what this was 2 ticks ago, right? But the problem is that if we do that, if we just take this input and feed it directly here, then in clock cycles 0, 1, and 2, we'll actually be overwriting the code. So the whole point of this adder is not actually to add 2, it's to make sure that we don't write in the first 3 steps. So if you step back, notice this adder is getting a nil because the address that we've delayed for a few ticks hasn't arrived yet, and that way we avoid overwriting the code. So this adder makes me a bit sad, and I think there's some potential perhaps for removing it, but I don't know how. Anyway, and then the other thing that I did was I realized previously I had been adding together these 3 outputs and checking whether the result is 3. So that was what I had a 3 in here for. But that took 2 adders, a comparator, and a 3. And I realized, oh, I can do the same wide equals trick. I tried to do a wide equals before, right? Where I said, let's check whether any of them are equal to 1. And that was how I found out that this wide comparator is like an OR, not an AND. It checks if any of the inputs are 0, are the control signal. And so then I gave up at that point and said, well, I'll just add them all together and check if it's 3. Very sad. But actually what I can do is say, are any of them 0? And then if any of them are 0, then they're not all 1, and I can pass that along like so. Which leads me to the last thing that I would like to get rid of somehow, is this input selector. Right? We basically just have, like, if the input is 1, output 0. If the input is 0, output 1. And that kind of sucks. Like, I wish that I could get this comparator to output the opposite of its result. Which is what I tried to do the first time when I said, are they all 1? Because then I wouldn't even need this input selector. I could just feed this comparator straight in here. But I don't know any real way to do that. So we're stuck with this for the moment. Still, a big improvement on what we had before. It is what is currently marked as ideal. I'm still not totally convinced. It feels like one of these 2 modules could maybe be removed. And I'm not sure how. Maybe it's impossible, but we'll see. Okay, and then the finale of this, not of this whole episode, I don't think, because we're going a bit quickly, but of this review of solutions I improved off camera is FauxReg. The one that started this whole thing when I sent him an incredulous email and said, how on earth can you do this in only 6 modules? I have 14, and I can imagine removing maybe 2 of them. Well, actually, I said also that I had used sort of a rehash of my first solution to basic CPU. Remember where I made it a 2-stage pipeline by having an alternator that determines what phase you're in the pipeline with input selectors based on that. It was like a whole big mess, and I didn't, just like it was wrong for basic CPU, I thought it was wrong here, but I couldn't figure out how. As an aside, notice these wires. Don't they look cool? I had mentioned in a previous video that like there was no way to wire. That I thought in the dev blog, Pleasing Fungus had said there was a way to route wires manually, but I couldn't find it. And he told me that if you mouse over a wire, it tells you. Which, like, I don't know, great, I guess, but why would I ever mouse over a wire? What information could it possibly give me? Well, that's not true. I do mouse over wires, but when I do that, I'm looking to see what lights up. What are the 2 things connected? And then the tooltip is just getting in the way, and I'm like, get out of here, tooltip. I don't want to see you. So, one thing that I might suggest is make this tooltip have some delay. Like, it's nice that it pops up, but sometimes I'm like trying to look at one thing and it covers up a different thing, and like I have to figure out where can I put my mouse that I can see the 2 things I'm trying to look at. And if this pop-up just didn't appear right away, but appeared after a little while, I could first see, hey, those 2 became blue. And then, if I really want to know about the wire, I can leave the mouse here for, I don't know, 0.2 of a second or something. Doesn't have to be very long at all. And get the pop-up. So, I don't know. I'm not a game designer, but I play one on TV, and so that's my advice. Or not my advice, my feature request. Wouldn't it be nice if I could somehow see tooltips and blue things at the same time? And then my dumb idea of how to do it would be like, hey, what if the tooltip waited a while? Anyway, so back to this solution. Isn't this so much smaller than the last FauxReg? I don't know what episode it was, but if you guys want to go back and laugh at the old one, feel free, pause this video and come on back when you're done. So what did we change here? I don't even remember. The old solution was so bad. It had like alternators, and I guess what we were doing is each step we read address 0, and then we transitioned into phase 2 of the first cycle, where we then read address 4 and grabbed the thing we had saved in address 0, or as the result of address 0, and fed it to this guy, basically. So that all was like a marvel of engineering, but not actually good. And what I've done here is the good thing, where we just have a clock that goes up by 1 every time, and we're reading the address at the base address every time. And all we do is we just put it in a register. It starts here, goes to here, goes to here, gets delayed, gets delayed, gets delayed, gets delayed 3 times, and then finally gets written. At which point, we have just read, finally, gets delayed 4 times, I should say. At which point we have finally just read out of memory the address that we need to write it to. So this one doesn't start writing as soon as the previous one did. It doesn't actually write anything until cycle 4, whereas the previous one wrote as early as cycle 2. But we're still writing just on exactly half of the cycles, which is the fastest you can possibly go, because you have to read memory 8 times in order to write 8 things, and we were doing that. Reading 8 distinct addresses, writing 4 distinct times. It's just it was on stage 1, 3, 5, and 7, and now it's on stages 4, 5, 6, and 7. So, okay. Anyways, this is a pretty powerful technique that seems a little bit, like, kind of lame. Like, shouldn't I be charged for wires or for the size of my registers or something? Just saying, hey, this is as expensive to put in as this? I don't know. That doesn't seem quite right. But whatever. I mean, it's a game. You pick something to optimize for, and then let the creativity of the player fill that space in whatever way they can. Even if rules kind of seem dumb, having those rules and constraints in place leaves you room to maneuver around them to do interesting things. So anyway, that's the solution to faux reg with just 6 modules. Isn't it lovely? And I definitely did not solve any more puzzles. Delay jump we could go work on, I suppose. But I think that I would just like to finish up the asides. Well, not finish up. Divide's still here. I think the rest of this asides board is all done in a perfect amount of time, or modules, right? Except for greater, which is better. Haha. Yeah. So let's just grab full CPU and see if we can knock that one out. So I assume we're going to need something a lot like branch here, so let's grab this. Okay, so what is the new thing that we have here? Add, load, jump, branch. Well, it's not so obvious, is it? What is new? I think it's load, because there's no input going into this load. But obviously, we definitely need to set a register when we're loading something, right? So, now, do we have save implemented somewhere? Yeah, save is already implemented. And we already have our jump instructions, jump and branch equal implemented. Wait, what? Oh, interesting. When we copied this, so the parts that we pasted in are not exactly the parts that we copied, of course, because this op selector knows what kinds of instructions will be in memory and has slots for only those instructions. So it gets a little bigger every time you copy it into a puzzle with more instruction types. But it has kept its connectivity, so we've gotten into this like invalid state where these two nodes are touching, but they're not connected, and this one is connected to here instead, while this one is connected to here. And that's correct. They are wired up as they should be, but they look wrong, right? So I'm just going to move it like so, and go check the other op selectors, see if they have any dumb things. None of them are actually bumping up against an instruction, so an input, so it's fine. It's just this one that was. And of course that was fine too, in air quotes. But this is nicer. Fine. So I think all we need to do is implement load, which should be like really simple. We'll just say, okay, what do we have to do in the case of load? Set register 4, that's dest, of course, good, to the value from the memory slot in target. Well, that's pretty easy, right? Which one of these reads target? It's the top one. So we'll just create a reader reading from the value in target and put it here for load. And I think that's it, right? Let's find out. Test. We'll just fast forward to the first load, which is instruction here, okay? And we're saving the memory slot specified by register 3, register 0, 1, 2, 3, that's 50. In slot 50 is a 5. So, great, that sounds right. And we'll just hit play. And I don't really understand what program this is doing. Wait a minute, something's wrong. It's not going anywhere. We're stuck on this load forever. Why? Come back. I hit the wrong button. This counter is not advancing because we need to feed it an input for load, which is the same as this input. Great. We need to tell it after you've loaded it's okay to move on to the next instruction. Yeah, and now we have indeed done that. This is slow. I mean, I don't know. I could drag it around. Sure. I'm done watching. Show me the answer. Done. And 4 a.m. No point going home now. I'll just hit the couch. Hard to fall asleep. I worry sometimes, all the chaos and injustice in the world, and here we are just building chips. Whenever I talk to Laszlo about it, he laughs. They're wasting their time. We are the real revolutionaries, not these long-haired kids wrecking the schools. Wrecking the schools. Okay. Well, there you go. So we are now done with the asides, except for divide, which will probably prove a challenge. So, do we have time, do you suppose, to solve a 3-star puzzle? And my guess is probably no. So, I'm going to say, I mean, obviously, I could record an 8-hour-long episode if I want. There's no hard time constraints, but it's nice to have these in little bite-sized chunks, I think. Half an hour to less than half an hour is ideal. At 40 minutes, I've usually made a mistake. I remember for Crawl, I used to upload hour-long videos and be like, oh, geez, it's getting up to an hour, better stop. And, like, I don't know, that's fine, but I think it's kind of nice to have these a little bit shorter. Anyway, all this blathering about YouTube, who cares, right? You guys are just watching videos. And here's me wandering on and on about what it's like to record. So, with that, I guess we really are done, and I can stop talking. Thanks for watching, and I'll see you next time.